I want to just review this whole peripheral nervous system more. It's an emerging field, so it may take a while before some of these things become ubiquitous, available in India and elsewhere. But I think it does hold a very high clinical potential. So, the entire idea in neuromodulation in a periphery is and it's usually electrical, because so much easier to manipulate electricity compared to other, but people can try other approaches. That what you do is to try to interface to the nerves by stimulating and recording. In ideal world, you would do a closed loop. I think it's very ambitious, because if you consider pacemaker, it's not exactly closed loop, or deep brain stimulation. It's not like it's sensing dopamine level and doing something, right. So this is a very ambitious overall idea. Just when you have a migraine headache, and if you stimulate the nerve to reduce the migraine, you don't need to have it closed loop like sensing. Thank you so much. So this kind of a system can be initially open loop. Yes.
Pacemakers could be said like closed loop because they are also detecting the beat.
So you got me. You're quite right that pacemaker are actually closed loop, because they are sensing the electrocardiogram, absence of the heartbeat, and stimulating. So you're quite valid. So let's say the very first pacemaker, very beginning when they were introduced, they were what I call asynchronous pacemaker. They just stimulated it, right? And then it became, because that was just a pulse generator. So in a way, first of all, I agree that you're right, and pacemaker may not have been the best example, but I try to give it as a way to simply understand it. But for a deep brain stimulator, of course, during implantation they are testing when you have tremor, where should the electrode be. So to that extent, during the surgery it's closed loop, but later on, that's it. It just, you stimulate when you want to reduce tremor. Otherwise, if you're sleeping or something, keep the stimulator off. So nerve stimulation or things like that, there are these for inflammation and all of that. Occasional stimulation seems to have been enough, so you don't have to close loop. But epileptic seizure probably should be closed loop, because you detect onset of seizure, stimulate, or predict onset and stimulate. So it's a closed loop. So I'm just saying it's just more ambitious, because recording from nerves is very challenging, very difficult. So if you look at some of the data, actually pretty high level of numbers, but spinal cord tends to be the biggest, because that I told you, like spinal cord pain. So spinal cord pain and other discomfort, and then of course spinal cord injury related loss of bladder and sexual control, and all of that means that it's a bigger market, and there have been more companies and others involved in it. Auditory nerve stimulator for hearing. So now this is a cochlear implant which is for hearing. One of you did ask question at point about balance. So that's the vestibular system in the ear, and that controls the balance. And there is a clinician scientist at Johns Hopkins who is one of the pioneers in developing vestibular processes to restore balance for people. There's a disease called Meniere's disease, where some of these hair cells all get affected, and there's a balance problem. People get vertigo. Would they implant a extremely elaborate? He's been doing that research for almost 10 years, although trying to develop it on the side, tough. Then deep brain stimulation for tremor and Parkinson. I'm actually surprised the numbers are so small, but I think it's to do with brain surgery and all of that. Vagal stimulator for epilepsy. That number is even smaller, because most of the epilepsy, the numbers are very large, but most epileptic patients are treated with drugs. Although when I remember when I was young, and I'm in hindsight, I remember there was some neighbor, a lady used to, surely now I think she must be epileptic, but in those days, there were all this notion that she is having fit and she is having some demon and something is happening in her, or in other situation something, she is, they pray her, and because her behavior is something people couldn't understand. There's kind of lot of misinformation associated with epilepsy. but by and large it's treated with drugs, and if it drugs doesn't work, then device, and then after that surgery. And then sacral nerve stimulate for bladder. So I gave that some example of how it's built. These are non-invasively stimulating to control the bladder, because invasive surgery is very doubtful. Even the clinicians we have talked to, they have not been so keen to mess around with nerves and do implantable surgery. And then phrenic nerve for respiration, but still a number of new ideas that keep coming up. And this area has started to get a lot of publicity and press, and so it's seen as a revolutionary therapy in prayer because of there's so many nerve and nerve functions can be affected. So there are many targets: depression and panic disorder, rheumatoid arthritis, which is kind of interesting that you stimulate, the message goes to the brain releases chemicals that affect your arthritis in the limb. Very strange and odd way to do it. Obesity, I told you that Rose company and FDA had given approval, but now I don't know whether, to my knowledge, I don't know if it's a very successful product, because eventually to treat obesity, would you go and do a brain surgery? So maybe that or the cost. So how is this generally implemented? So in case of bladder, right, this is a picture of a bladder. To build a closed loop system, I mean, these people have a recording, these are the recording electrodes, and these are the stimulating electrode, and all these nerves, pelvic nerve and pudendal nerve, they are coming out of the spinal cord. Of course, the picture is kind of distorted, it's a little idealistic. In reality, these are really close to the bladder, the spinal cord is kind of far away, but by recording and stimulation, they are controlling and emptying the bladder. In my own research project, one of my postdoc is using pressure sensor and a bladder pouch to compress the bladder. So both are possible, but again, it's at a very early research stage, both of these. What is commercial stage is a device like this, which is a pacemaker like device. So company like Medtronic and others have an advantage because they can recycle the device. They have already solved the problem of titanium can and connector and all of that. So they don't have to go that extra level to prove the regulatory approval and safety and all of that. And then they adapt the device. Obviously, if it's for bladder, it may, the size of the device shape may not be the same that can be used for pacemaker, but if you adapt, it will be cheaper. They may customize to make more profit, it's hard to know. But what they have done in this case is that a matter of emptying the bladder, it's human activated. So when a person, overactive bladder, then you stimulate and the urge to go is suppressed as long as stimulator is on. Or underactive bladder, okay, I'm ready to empty the bladder, turn on the stimulator, the bladder empties. So it's under manual control, and many people with disability or older may not be able to do that, but it is a practical solution. And as I said, recording from the nerves and all that is quite difficult. So this one is just a implant a stimulator to empty. And I told you about vagal stimulation. So in this case, they have done again the same thing, semi-invasive, non-invasive. If you can get away with improved mood and other symptoms for long-term depression. So you don't need to have it on all the time. You don't have to have it closed loop. I'm very depressed. I feel like God, the world doesn't like me. I should just die. Depression is terrible. It's huge. Percentage are very large, even in student population. I was told like some number of suicide in IIT Kharagpur are shocked 5, 6 a year. That's like a shocking number if that's the case. So a lot of it comes from depression. Depression is because of social pressures. So there are many types of depressions. They are acute that young people might have, but chronic depression, people just don't get out of bed. They don't want to go anywhere. So then a device like this is turned on, and if it affects the mood disorder, why not, right? As I said, there are drug companies are investing in that, because if you do a drug development, it's a very expensive thing. drug on millions of people, and it's just very expensive. You know, you have to test it, and you know, so drug companies today say that to develop a new drug, the number keeps going up. It costs say $500 million. Maybe numbers is approaching billion. It is to be questionable. That's how they justify the high cost of drug, that they have to recoup that cost, the profit. So now 10, 20, 50% of the cost of medicine is the money they spend on research. The problem, their justification, which is reasonable, is that very small percentage of drugs really succeed. Sooner or later, through some side effect, some complication, it fails. And so it is a costly affair. Whether it's this costly and all that, unclear. And drugs have side effects, right? If you have seen any drug advertisement, at least in US, you say this drug for this treatment, and then the next 5 minutes they're telling, don't use it if you're pregnant, don't use it with old, if you're young, and if this and that, until the drug is final. You know, I mean, they speak very fast, you can follow, but that they're doing it for legal reasons. The devices sort of have an advantage that once their reliability is proven, you can turn it off. If a pacemaker doesn't work, just turn it off and let it be. Same thing with deep brain stimulation. So devices offer some advantages, including that of cost, in the sense of it's a one-time cost rather than recurring cost of drugs. So that's why some company like drug company like this is getting invested in this field. So this is a company, Setpoint Medical, came up with this inflammation arthritis. I think the font is even too small for me, but yeah, maybe when I distribute it, you'll be able to read it. But again, they are the ones who develop this treatment for inflammation and arthritis. Oh, repeating, some slides are repeating. Okay. There may be others for cardiovascular and metabolic disorders. So you can do this closed loop stimulation for autonomic control of heart. So sympathetic and parasympathetic. So sympathetic speeds up the heart rate, parasympathetic lowers it. If you can do something like that for blood pressure, would be even more fantastic. So you know, there are many number of these kind of examples. So this one I think is for targeting rheumatoid arthritis with so rheumatoid arthritis. This is the paper published in Nature by this Setpoint group. The vagal stimulation reduces inflammation. So you know, it's quite remarkable, right? And so you see again, I'm sorry the pictures are very small, but they came up with like a cuff-like electrode in the nerve. So like do an incision, put it in there. A device is implanted somewhere very small. Everybody likes it here because there's a lot of space in this area for even pacemakers are put there, and then run it through the neck into the nerve. For epilepsy, again, same idea. And so weight loss, FDA gave an approval for obesity. This is targeting sleep apnea. There is a nerve called hypoglossal nerve, and so this kind of nerves either affects your pharynx or affect your diaphragm. So I don't exactly know what the target here is, but the same thing that you hypoglossal, because sleep apnea means particularly like infants, although this surgery and all that would not be done in infants. In adults, you know, they tend to stop breathing. There are companies that have come out with some device that puts on your nose and somehow they say it helps. How you sleep helps. But sleep apnea is a serious issue. As I told you before, children have died and parents have been blamed for killing them and so on because they just stop breathing. And so this, again, it's the same kind of pacemaker like device with the wiring, and things go and then they nerve stimulate. So now what you realize that after all this first round of stimulator, hopefully in future it will be bidirectional closed loop, which means you do record and stimulate. So you know, we will be developing devices that are therapeutic, first of all, detect and treat seizure, detect and somehow close the loop, and subthalamic nucleus for Parkinson. The prosthetic is obvious sensory and motor, and then who knows, someday repair of the brain function as well. Now for reviewing, the technology, as I said, I like to review again and again to reinforce the electrode techniques like this to wrap around the nerve. IC chips, this is a 4-channel stimulator, 8-channel recording chip, the coil and so on for energy harvesting. So, you can do wireless, they can be bigger, they can be miniaturized, but these are the key building blocks of these implantable device. And that is why in one of the things we implemented is this kind of energy harvesting coil, and then all the chip and electronics here, and then interface to the nerve, and then whole idea is to develop this sort of closed loop solution for pelvic nerve in a single system. And you see here is the intra bladder pressure. So whenever there is this one is detecting the void event, and then you turn on. So, this is on and then this is off, and so you turn the stimulator on by looking at the bladder pressure level, and sometimes it works and sometimes of course there are spontaneous changes, then it is a problem. And then systematically each time you look for the real sensation. Now, this is the true event, so you stimulate and empty the bladder. So now that is working. So, now it is a here is a stimulation and the bladder pressure went up, and so of course there can be emptying corresponding to that. Again, stimulation comes on, and you will see the bladder emptying. So, this technique works. Now, to take it to commercial application, it is going to be an extremely long road from a lab prototype to a clinical device. Okay, I think this is these are then peripheral and so on. So, for the limbs also, by the way, there are some developments where I think there is a group in Italy as well as in Europe, US, they are doing it so that you can record for brachial plexus and so on, 4-channel radial cuff. So, these electrodes are on the nerves. In this design, they still have an external stimulator, so that you can now provide either motor or sensory information. So for an amputee, this is the electrode array, and then will provide the stimulation. So there can be similar solution for head injury as a proof of concept, traumatic brain injury, right? You get hit with a ball, traffic accidents, which is very common. So, some part of the brain could get damaged, right? I mean, and so how, if the part of the brain get damaged, one is the plasticity, but can you kind of bypass it and somehow improve? So, this group in US developed this kind of a bidirectional device. So, it is a small microelectronic system. You can see compared to it is almost like the size of old rupee coin. So, very small, all the electronics is implanted. These are all microcontroller and all the microelectronic circuit, and then they tested in the rats. So, the device is on the head of the rat. As I said, rats or monkeys do not mind anything on their head, but if they are anywhere else they do not like it. So, the device can easily say the rat can do its own thing. So, I am going to show you some videos, but this rat has this device, the wireless, you can see the antenna for electromagnetic and so on, right. Okay, so this is a kind of normal rat. Okay, so it's given these little pellets, little bit of food, and it's pretty dexterous, right? It goes out, and so that's how you can test the rat's dexterity, because rats are otherwise going to run around and so on. So by this is one of the tests that's developed. For monkeys, it might be they are smarter. They can press buttons, do other things. So, with the rat you do this kind of thing where they must show some dexterity and some intelligence to go through the gap and then go through the gap and receive that pellet, right. So, some sort of hand dexterity. Okay. Now, what happens is that this rat was given, so sorry, I need to back up here. So, here now you can see that it is starting to struggle. So, when there is a lesion in a motor cortex, then if I back up here, it was kind of struggling, right? See, it's not finding its way through the gap. In the before, okay, maybe here, right? Earlier on, okay, so this is where the lesion is, but before that, no problem, right? Just go in, grab it. But when the lesion occur in the head, lesion in the motor cortex, then the rat is struggling. It's motor coordination. That's why I was saying, right, for humans who might have an injury like that, they can see it, but they miss the target. And so this kind of problem in the rat is either slower, it's struggling, cannot find the target. It's the same rat, but you see the behavior from head injury. And then continuing that, now its device or stimulator is turned on, and so you will see the improvement in behavior. See, it's slower, but somehow it has succeeded, because what they did is to record some part of the brain and stimulate it and bypass the injury area. So there is some improvement. I think there's another. This video might be more informative. You should be sitting and thinking, wow. I mean, like you're preparing the brain. If you consider that, that's so amazing, right? That the rat, it's a rat, it's simple task, but through electrical stimulation, you're repairing essentially the function of the brain. So isn't that quite, to be honest, quite amazing? Okay, so you see general idea that this, all kind of possibilities. You're treating and repairing the brain. I think the video probably still going on. Yeah. It's slower. The function is never the same as original, but the decision power and ability to target is so much better. So we need a lot of these kind of devices I've shown you before, and eventually commercial devices would look something like this. So this is the great new frontier of peripheral and visceral nerve. There are a lot of research funding across the world and all of that. So some of you in next generation might do that. All right. So this is something left over from yesterday. So I think what I want to do is to take a break, give you guys, and then we'll go into neuromorphic engineering. As I said, in the morning, next 2 lectures, and afternoon 2 lectures will be cognitive, and then we'll have a little bit of longer lunch break today. Okay. So take a little 15-20 minutes break. Looking at your lips and sound, you're doing better. If you're not, both your ears, close one, you might do much worse, So understand how this is, it's a speech, but there is your brain, your neuromorphic is at work. Okay.
Cognitive science come together.
All kinds of people interested in how the brain works.
We're trying to understand how to build cognitive systems.
The neurons are people who are interested in two fields, which are normally very far apart from each other.
Their common interest is really in trying to understand how the brain computes.
Are those that actually started using technology to make artificial systems, actually looking at the brain and the neurons.
In these 3 weeks, we get all the people, all the neuromorphs in the world that work on these things together, and we exchange ideas.
We have engineers, we have biologists, we have neuroscientists, we have people who are really involved in different areas in their home.
So what this is that in this topic of neuromorphic, how brain works, can we model it into circuits, can we make sensors and electronics out of it? And it intrigues and interests a lot of people, and what they're saying is it interests neuroscientists in one way, mathematicians in another way, engineers in another way, all of that. And this particular video and picture is that this meeting takes place in July, to about 3-week period in Colorado in the mountains, beautiful setting, and everybody sits, works there, exchanges ideas, give talk, and brainstorm about it. Also, people do projects. So I'll talk about a little bit. So like I went there once and I did I work on touch and say how do I make biomimetic touch sensor. But that is what this kind of comes out. This is one way to, and again it's all a very rational engineer. Maybe late evening night over wine, beer or Coke, they are having discussion about life and death and all those things. But again from rational thought of, okay, so I'll play this again.
Institutions. And so kind of the idea really is that we can take this opportunity to play around and learn a lot of different techniques from different people.
Some people want to make things that work in the real world, want to make products. Some people are interested in just understanding how the brain works, and they use the technology as a tool to make progress in basic research, basic science.
What makes our group unique really is that the things, the models that we're trying to develop or understand or implement really we're trying to test neural algorithms in practical situations.
Why are we doing this at all, right? Why this is useful at all? So there's the obvious answer is to understand the brain, how we work. And that has tremendous implications. It has tremendous implications when you're talking about computation. We are tremendously effective and efficient in many tasks that computers fail.
So actually behind that was like a little humanoid little baby, and some of these folks want to build robots that act and behave like humans, like a little baby. Maybe not a bad place to start. It's eye movement. How does our eyes move and saccade and nystagmus and all that in the eye? If we can model it, the robot will be more human-like, And so all of this area, as they said, it's part fundamental, trying to figure out how brain works, and part practical, right? Like, can we make a practical robot?
Humans or animals, dogs and cats and so on do.
We're trying to understand how, when you make a motor system move the robot, how it feeds back directly in real time to the sensory information. And oftentimes what you find is that when you have a robot interacting with the world in real time, the problem actually changes.
How do you build machines that can really, work in the environment the way that we do?
Okay, so you get this idea, right? So that means there's neuromorphic is learning about how things work. So one of the fundamental thing, we have this, we can look at brain, these neurons, 3D, whatever it is. So it is, well, I don't know whether it's the fastest, but it's a kind of a supercomputer. And we can make it into electronic one, and there are some graphics and data and slides. So 100 billion neurons to make 100 billion transistors is nothing, right? So that's not the thing. 10 to the power 15 synapses, that's out of our reach. Make it into 3D, most of our circuits are pretty much by and large 2D. Can we make it in vastly, each neuron connects to 10,000 other neurons, which means that's just the average number, so impossible. Or wiring, we just can't do it at that level. That wiring is just not going to happen. But the biggest and most fundamental difference tends to be that whatever this computing, it's doing with so little power. This is doing, although about 10 power 4 or 5 order, 10,000-fold more consumption of power. So there are a number of reasons why, and then of course it's incredibly adaptive and plastic and so on. So can we get to it step by step? And so so idea of neuromorphic is to mimic the biological computation. Now some people do it very, very precisely at the level of every ion channel. That one time I showed a circuit of synapse, sodium, potassium channel go down to real precision. So one of the, and you will hear about that later, this human brain project sort of is taking that path, that let's make it as biomimetically as we can, so that brain is that computational brain is so much like it that if I apply now artificial drug to it, I should be able to test the behavior and reaction. Others say, I just want to do computation and intelligent solution, so I don't need to do biologically precise. Well, let me do what is essentially important: on-off, spikes, action potential, conduction, synapse, synaptic learning. So there are two approaches, and that's the IBM, True North, and those kind of applications. And the third group are very specialized computation for vision or something like that. Okay. So, but no matter what, then we would partly learn, because on a artificial brain, like computer, we can do experiment, right? We can try it. You want to simulate brain injury? All right, can I take out some of the neurons, artificial neurons, see if how the performance degrades? It might teach. What if the large network produces, once every artificial neuron is active, it will produce EEG-like rhythm. Now, what if I synchronize some of them? Would they produce epileptic-like rhythm? So, you can mimic that. What if I change the neurotransmitter model? Will it cause that? So, that's why interest in neuromorphic is both fundamental, how brain works, disease, practical, can I make smarter robot, and so on. So, it has been applied not just for computation, but vision, listening, touching, all of that, and maybe in some way make biomimetic. Like a baby is a good metaphor that is slowly learning. So, why not our neuromorphic computer implanted or inserted in the baby makes it action, and maybe it learns by trial and error over and over. And I wouldn't be surprised that this will get coupled with DPI, so that we can take deep prior knowledge to go even faster and be smarter. So, take the example of retinal processes. As I said, current retina, just stimulate it and you get pixel map. If sometimes you must have seen a computer video, computer screen and there are just pixelated information. But it does not talk about motion, color, and perceptions. And so, what if, and there is a lot of actually pre-processing is going on in retinal cells itself. So, it would clearly seem like a retinal process is not just a camera. It is a camera processor that has to do some information processing till it goes to the brain. And so, in that sense, retinal processes could benefit from neuromorphic, fully understanding how vision works, and we will show some example. Cochlear implant, same way, this is like the way cochlear implant works, right? This is the hearing aid, but then this is the wireless device that is stuck here, and its partner, the receiving coil, the transmitter is outside, receiver is inside, relays the information and transmission, which then goes and stimulates the cochlea, and that is how you hear. Noise cancellation, speaker recognition, we do not have any, right, you are all able to listen because you could see the tongue moving. That information is not available to somebody with a cochlear implant. 2 years working together. So, cochlear implant could become more intelligent as well.
For the first time, IBM scientists have created randomly spiking neurons that imitate the functionality of biological neurons. Now, this is a big breakthrough. The technology could be a game changer. For example, it could lead to the development of neuromorphic computers or brain-inspired computing, which was envisioned way back in 1980s. This research will be published in the Nature, and IBM has also patented the technology. Now let's see what IBM has actually accomplished here. Electronic circuitry is largely deterministic. The same set of inputs will always produce the same set of outputs. But brain cells, being living things in their own right, seem to have a mind of their own. Brain cells exhibit what is known as stochastic behavior, and now scientists at IBM have captured the very essence of what makes a brain cell tick in an artificial neuron.
Lot of
By
hyper.
using a phase change material such as chalcogenide, they have been able to faithfully replicate stochastic neuronal dynamics observed in brain cells. Essentially, a phase change device at nanoscale behaves almost exactly like the membrane of a brain cell. Each artificial neuron consists of inputs called dendrites, a body called soma, and an output called axon. The soma functions as a processor which receives inputs through the dendrites and then generates an output on the axon. Just like its biological counterpart, the artificial neuron receives potentials from the dendrites and integrates them using the patented phase change device. Each input pulse causes the phase change device to heat and melt a little, leading to a change in its physical state. This in turn gradually increases its electrical conductance. So as multiple input pulses arrive, they cause successive increases in electrical conductance. The overall conductance of the phase change device increases till the threshold point is reached. Beyond that, the phase change device fires a spike and then is reset to a non-conducting state. Now we will see the crucial feature of this patented phase change device. The nature of phase change material is such that after being reset, the artificial neuron is in a slightly different state than before the pulses arrived. This feature provides an inherent stochasticity or randomness to the functioning of the artificial neuron, making it work almost like a real brain cell. This technology could speed up cognitive computing and could also be used to analyze Internet of Things big data. Please do share your thoughts on this technological breakthrough in the comments below.
Okay.
Until next time, keep innovating and keep patenting.
I'm awaiting comments. What do you think? Is this the brain? Is this a breakthrough? How many think it's a breakthrough? Nobody? Come on, guys. Give them a break. So, few of you. How many think it doesn't? Rest of you don't have a brain. Well, anyway, I'm just going to relax with that. So, point is, it is a bit of hype. Yeah.
In that coma, was it so simple it's only receiving and passing it on?
Well, that's why it's a lot of biology research or a lot of engineering transformation is a extremely high level of reductionism. So, as I said, this kind of neuromorphic, it took the most essential principle that we understand so far. We have a lot of other things understood, but they can't implement it. If they do it, it goes crazily complicated. That's why I'm saying Europeans took the opposite path. Everything must be there. This one, the basic idea is if you give an input, a whole bunch of them, sum it up, there is an output. There is a bit of that kind of stochasticity. That's what they are emphasizing. So, there is a bit of randomness built into it. You never do this same way again, you know. Oops. Yeah, there is a randomness to everything I do. So, there is a bit of that, and the hyperbole, they are showing it off.
So it's not a breakthrough.
Well, you know, that's why I'm saying I use the word hyperbole. It is the way scientific press does it. We don't want to get cynical about these things, and that's why I didn't actually debate that question. It's great to have an awe and appreciation and curiosity, you know. That's great in their own way. And I know the press person who is a news reporter, to get our attention, is of course going to say all this in a big loud way. You know, that's why you are boring. This is not a breakthrough, and by the way, this is just an incremental result of this. That's a dumb, stupid chemical that does a little bit of that. But IBM, you know, you're going to stop tune out, right? So it is a way to stimulate. But so appreciate the beauty of it. But basically, it is a step, and I haven't seen that actually. The current IBM True North and all is not that. But that's nice video clip to show. There may be a lot of others. So,
From which country? IBM from where?
I think this. I mean, IBM is one of the main research centers in Almaden in New York, but they also have Zurich, and so I don't know. This one just happened to be something I had it. It's not very current. Actually, the current approach is no longer that kind of a material, so I think it's probably petered out. It's just nice discovery of these phase change materials. More popular that a lot of companies, IBM, HP in particular, are pursuing is called.
Compared to this one, your Exxon was far more better working.
No, it's not mine. I mean, it's not. It's an option. Like I said, it's a way to mimic something. The more current one, there's something called memristors, which is, again, you want to make change due to input. And this memristor is a way that transistors resistance changes with input, and in a way you builds in a memory, and it's very attractive to put it in silicon, in electronics, and it's very popular nowadays. But what has happened is that every time people come up with this, these are very special electronic processes. They don't scale up. They don't make manufacturable electronics. And a good old standard silicon way of fabricating wins out every time, because silicon industry is so developed. Hundreds of trillions of dollars have gone into specializing transistor, making them smaller, making these VLSI chips and all that. So they can do same thing brute force in silicon and in software. But the beauty of this thing is to trying to get these such ideas in hardware. But they only capture one facet or the other, such as phase change, stochasticity, another one change in resistance. Some others might produce stochastic spiking output and all that. Okay, so just take it in a kind of spirit of that. So let's consider the vision, right? So here you see the picture. What you're seeing a video of this camera. That again, let's just go back. In a lab, we are throwing an object in air. You can hardly see it, right? So much clutter is there. This camera, all it does is looks for motion. So when it looks for motion, everything else looks gray. There's nothing happening. And the black and white correspond to motion towards you or away from you. And because going in spiral, you see that. Plus, I have all the digital data available, so I can completely recreate its trajectory. So all I wanted to do was to look for a moving object, kind of like the example of the frog looking for a fly. This would work beautifully. It doesn't have to process all the background and this and do pattern recognition and all of that, just look for moving object. So that's why this is what is called dynamic vision sensor. Its pixels are looking for change in optical signal. Very good for something. Imagine you want to track a ballistic missile coming at you. Clouds, other things, birds, noise, you don't care. You're just looking for a small, pointy, fast object at super high speed. Well, any camera coming at you will have frame rates, right? You know what a frame rate is. Every camera blinks, takes picture 30, typically 30, nowadays 60 to 120 frames a second, but that's still like 10 milliseconds. And a missile speed, you might need microsecond. This camera is always on, so may be very useful such application. So how neuromorphic system would work would something like this. You know, you have a camera with a CCD or MOS kind of a input that takes the light, but just like in our vision system, there is an input layer which is a transistor that looks for on event or off event, and then various layers of processing such as for motion or direction or edge, and then final part. So kind of like a neural network, but can be very readily put in silicon. And an ultimate way might even be classifiers, so they can make it a face or something. So how will it work? So this is the main explanation of neuromorphic, right? So you have all these pixels. Light hits something, there will be of course some synaptic delay, but it will hit the ganglion cell, some neuron. So that from rods and cones with a delay will go to the neuron ganglion. In electronics, it will be that MOS transistor goes to the processing transistor. There can be many of them. This one then is particularly specialized in direction. So any one of these neurons will be active based on the direction it sees. So now this will happen all in parallel. Every one of those pixels will be giving this information. And so you know you'll have a tile of these neurons passing this information as spikes, lots of dots coming at you. But they may be quite silent if nothing, no change or direction. In this case, direction specialized, other one can be motion. There won't be any output. Then next layer has to do some processing, as I said, for direction or motion. And that's way step-by-step processing is done. The resolution is fabulous because essentially this microsecond only comes from the delay in the transistor. Now compare that with the delay for even tenths of millisecond, and frame rate camera also. So these things don't have frame rate; they're just continuously producing the signals, and it's asynchronous, which is important. Every pixel to itself, right? If you look at the CCD or MOS camera, they all work, and they have to be sampled. Those who are computer oriented realize that you sample the information. Again, sample it again, 10, 30, 100, 1,000 times a second. Here, there's no sampling. Information is coming at you all the time. Do what you want with it. So it's called asynchronous. So if some information like this is coming on, how do you produce spikes from it? So they said, okay, if the information is, the signal is going down, I'll give it a negative spike. If it's going up, I'll give it a positive spike, and so on and off. So in a video sense, if the object is going away from you or towards you, you get positive or negative spike. And so the color coding is like that. It's just every color is actually a pixel, and every black means, let's say, coming at you, white means going away from you. There is a, it's just a way to colorize it so we understand how spikes work, but oh, my battery is low. Oh boy. Can one of you help me with this? What happens is that I think yeah. I think that's sort of, you have to, you have to press the upper hole. Yeah, good. You know how that is. Wonderful. Okay. So can you just make sure the light is on? Okay, good. So we see now it's built in to produce digital data, these spikes, so that you can sense the motion. No frame rates, very fast, and the spikes are now shown as x, y, p, probability and time t. So you see, now you move the camera. Of course, you can move the object, and you can see very naturally it's actually picking up edges, because edges where the motions are occurring. You can see the white and black actually sometimes flips. So let me play the video again. You see sometimes the same edge is white or black depending on the direction of the motion. So like this so-called event driven or neuromorphic sensor produces this kind of information. Again, to repeat, every pixel is active, every pixel is producing spikes. If it's coming at you, negative, it's going away from you, positive, or you can reverse it. Information is as like an on and off, so it's spiking and digital. So camera is very efficient, because if there is nothing happening, you see this gray area, no processing. There is no frame rate, no nothing. It's just constantly capturing the motion picture. So it's kind of like specialized, but excellent for what it does. So now in this case, my PhD student postdoc put it on a drone. So if the drone is flying with this camera, it might see some scenes. I don't have the video synchronized, so but you can see, by the way, that there are cars that you can make out. People waving because they have motion. So you can capture the movement. Now movement can occur because the drone is moving and therefore camera is moving, or it can be because a person is moving. So you see some benefit of this kind of neuromorphic technology, that it is highly specialized, but it does its special job very well and might have some unique application. We probably, there are some people think that for retinal processes, this is where we have to go beyond just pure pixel information that current retinal processes gives, but that you have to give this intelligent processed information. So let's look at this scene, right? Very bright, shiny scene. Two people are walking very hard until, I put a green box so they can see it. Neuromorphic camera picks it up because it's only focusing on motion. So, the clutter of trees and branches, no, for us it seems easy, because we are neuromorphic. So, we see that you guys, while looking at those people moving, have ignored a lot of this stuff, right. You are paying attention to what you care. We tend to focus on interesting things, right. Most likely before the blocks came up, your attention went to the tree, a little branch here, a little bit something sounds interacting, you most likely ignored this, you ignored all this area. So, we have this natural foveal attention. Then on top of that, we tend, yeah.
Sir, we have a lot of image processing algorithms which can detect.
I understand, but amount of processing needed. Think about the computing power and processing needed. And this is a single little tiny chip does it. So, yes, every one of these has algorithms for attention, for shape recognition, face, texture. Massive computing is needed, massive computing. What we say, that algorithm we have to process this at real time, to process very significant computing is needed.
In my MTech, I designed an algorithm which can do it in real time and it does not cost that.
Yeah, well, but would you not argue that you need lot of computing? But look, I am going to come back to your point very well. Actually, neuromorphic people are still struggling to prove themselves against people like you, because what is happening is that the processing that you are taking for granted, what you are not recognizing is that you had a computer to you which was consuming kilowatts of power. It was, you had to write software, and it had to be an algorithm, and it had to be functionally designed and programmed, and you therefore solved that problem in a computer. Now, the good thing is you can write another algorithm for another application, but if all I wanted to do was to look for a moving car, this one single chip with 10 to power 4 or 5 low power in tiny little chip can do what would take you a computer programming, algorithm, coding and decoding. So, the point to be made about all these neuromorphic system is that they are very limited, but very good at that specialized function they can do. If you want a lot of flexibility, a lot of programmability, power is not a consideration, size is not a consideration, you do your algorithm, work on a traditional computer. Look at the real world reality. Probably 99.99% of the computers and something are like the way you are doing. 0.01 might be going towards neuromorphic, because at the end of the day we all want programmability, flexibility, and then you can also make argument that computing power keeps going up. So, what I did as a graduate student was so limited, what you are able to do is even better. Few years from now it is going to be even better. So, the neuromorphic technology is a niche. That conference where it said all the neuromorphic people come in, it is about 200 people. And maybe there are other 2,000 who couldn't come. Go to standard computer vision, there might be 200,000 people working on it. Commercial product, standard cameras, they are not doing neuromorphic, but every one of them are looking at it because of power. To put it in a tiny single silicon, they can't do it. And what's your biggest problem with your wonderful phone? Battery. Therefore, because it needs so much processing power. So, if you could, they could put neuromorphic camera chip that could do some specialized task, face recognition in a blink the way we do it, you save a tremendous amount of power and space and make the tiny chip work. So, this is why this consider retinal processes. Yes, I can design an algorithm and so on, but how are you going to program that? Here the retinal processes will get this spikes. So, that the idea is that it would be so there is a French company that has been formed to produce neuromorphic spiking activity, so that information is not pixel bright or dark, information is more and informatively processed for direct. I mean, they are still developing. So, whether it will actually human beings will pick it up as motion and color remains to be seen. But for sure that chip will be super low power, which means the retinal implant will work for a long time versus a conventional camera chip, processor, software, programmable. But that one maybe can be upgraded, reprogrammed. Retinal process on a single chip, maybe cannot. So, there is a trade-off. Okay. But you can see some specialized value. In this animation, one of my PhD students put this kind of camera on a robot. So, this robot's job is to navigate, and so static trees, and it is then eventually trying to locate the other robot. So, how do you do this tracking? So, you see that this is the neuromorphic camera, and it is creating a mental imagery or picture of the robot, and then there is a lot of the scene analysis, which is in a sense more or less irrelevant to it, because this is what we call predator prey. It has to go and find its target. Target is moving, it is moving. It's a very challenging problem, even for computer vision. People like you who do the conventional computer vision, two objects moving and tracking is a very hard problem, as opposed to recognition of an object, or that is the first order problem. Recognition of moving object is hard, because now you have to keep finding the frame. But if you are moving and the other object is moving, it's very hard, because there is a lot of relative motion, and you can see like things going up and down and so on. So, again, neuromorphic, because it rules out a lot of clutter and it focuses on only some things, has some advantage. So, the silicon retina only sees motion, see, and might be, hello, are you awake? You are seeing me, right? So, I am doing that. Are you noticing this? No, you ignored it, but your camera was seeing everything and processing everything, then detecting and recognizing and say it is not this, not this, not this, me, okay. Versus neuromorphic camera will come to this and focus only on getting your attention. So, there are some of these advantages on neuromorphic cameras. This student who did some of this, showed when they do testing, this is like a star-like object. See, it's beautifully, perfectly identified in the clutter. In software, algorithmically can be done, but this is happening in the chip instantly in real time. Or car tracking, you see, so much easier problem. Put it that way. Does this recognize anything else? No. A computer vision system or LiDAR system might recognize a lot of other things and process everything. This one is only processing this. Yes?
Sir, you said that when any object is like you mentioned in prey and tracking it, then the prey is moving, then you are able to track it with this camera. What happens when it is still?
Yeah.
How it tracks then? Okay, what happens?
What do you think Frog or anybody else does?
It has pre-stored imagery, so
Yeah, maybe so. I don't know about Frog, but I know what we can do, and that's what my student implemented. So, we have what is called saccade. Do you know what a saccade is, medical guys? So, eye has a little bit of that jitter, right?
Left and right cancers has
That's a little bit different, that there is a left right coordination, but saccade is just a shift, just a very rapid shift. So, eye is forcing a bit of motion. So therefore, in our visual field, the object is never static, because eye itself moved a little bit. So, what he has implemented in this is a bit of a jitter of the camera, and that way the scene moves. Actually, it didn't.
To generate the motion.
Yeah, generate the motion. Kind of like equivalent of saccade. Actually, it didn't really have to do much, because the robot itself was moving around up and down so much that relatively the other object was moving with respect to it. If the robot was, that's why I said a frog was not analogy, because frog was sitting and it doesn't move, and if the fish or or if the, let's say, I don't know, flower in front of it that may look like a fly or a photograph of a fly, it's not moving, the frog isn't going to do anything. But now if the frog moves and check, so that's why, right, we all move our heads a lot, right? None of us keeps our head straight. We move a lot, partly for orientation, but we deal with motion. Motion makes it interesting. Yeah.
So, motion is like things moving relative to the background. So,
it's one way to look at it. Yeah, that's exactly what's here.
So, when we are, you relative motion is all, I mean, everything is same with respect to us. So we
No,
don't
no,
need
no,
to
no,
track it.
no, no. It's jitter is just a change, right? So as long as you keep track of the frame and where the jitter is occurring, you have motion. It's a relative motion, right? Whether camera moves or the object moves, it's the same.
But
Whether
the input we are get, suppose we are tracking an object, it's moving relative to the background.
Yeah.
So we are able to look at it.
Yeah.
Now, if that object is stationary with the background, even if we move the
No,
source,
there is another thing going on, perspective, parallax. So with that parallax, the move of the back is much less, move on the object in the front is much. That's exactly, those are the kind of things is implemented to take care of some of the parallax. Okay, it's limited, but it's great. It works. It tells us, as like those guys with Neuromorphic said, some of them are objective to mimic and model vision, brain, nervous system to understand how we do it and validate the idea like human and visual basic neuroscience from spikes and all of that is coming alive as a chip. And some will use it as a car tracker, right? Suppose on the road somebody wants to see how busy the road is, so that road should be better maintained or toll booth or repair. You need to know how many cars are traveling a day. Can you imagine putting one of the standard vision cameras, doing a lot of processing with big computer behind, running the software? It's going to do far more than what's needed. Now, all I need is this one thing. As long as I can put the little green color, I don't even have to. It looks almost like a shape, like a car. I could just put a dot there. I can just count cars with a little tiny camera sitting there. Yeah.
So if there is another car and both of them are moving simultaneously, and for a particular moment this car stops and others start moving, then it will capture that.
Sure. I mean, every system, anything can be fooled. There will be exceptions. What if the two overlap? Right? There will be overlap, and in all computer vision, that's a huge problem when the objects overlap and so on. So it's a classic problem. People get around it, perspective, other things.
There are solutions for that.
Yeah, I mean each one. So, but they are unique solutions. Each one is a program, code, and before you know it, it's like Microsoft Windows. It becomes gigantic software, and there's big companies, Facebook and all that, they start using supercomputer. And even then, they may argue computer is going to get cheaper and cheaper. So no, so what? That's why I'm saying the neuromorphic is a great solution. They are hardcore believers, but it doesn't get commercial as readily. Companies have tried because when the solution is specialized, the market is smaller, and then the benefit versus utility is less. So that's why it's a half and half. Use it partly to learn about vision. See, what did you guys learn something about saccade right now? You learned a little bit about parallax. You learned about motion tracking as a way of vision works. You learned something about frog. So it's a learning phenomena of understanding how brain works, which is all we want to do. But after that, what can I do? Well, maybe I can make a better retinal processes, or maybe a surveillance system, or something to mount on a drone where power may be an issue. Although even that went away because the drone in its flying consumes so much power, the camera power is negligible, even a processor. Yeah, I wouldn't want to put a big computer there, but then you can argue that latest generation, some Intel amazing microprocessor might be so powerful that will probably do the job. So it's a bit arguable. Today, with wireless, anything can go in the cloud. So drone itself, if it's reasonably confined, can be talking to the cloud and getting all the information. So it doesn't have to necessarily have it on board. But in the right circumstances, this will have a value. I think this some kind of letter recognition and point tracking. It's just more for testing purposes. So now
this work describes a visuotactile grasp assistive system for upper limb amputee.
Let me
the
come back.
primary goal.
Let me come back to that later because it's
approach.
It's going to keep talking. Shut up.
The primary goal of this work is to come up.
It's a. I want to do this.
I think the microphone inside the group now.
Yeah, and now I'm of course messing it up. and our computer is going to complain and it's not going to come alive for a little bit. Because I want to do the tactile and then I want to come back to this. So, because it's about combined visuo-tactile. So let me just sort of jump ahead a little bit and not.
So you'll be showing us your lab online. You said some on Skype, something like that.
From here? I'm not sure. I didn't say that. I don't know what to do.
Something, if possible, if time is there, you will be showing some work, what is going on, or something.
Well, I mean, I did the first day that overview of SINAPSE, and I might repeat that tomorrow. See, that's why you see the power of repeating. I did show all the things. In fact, all this is, some of these are from my lab, right? This neuromorphic drone, but it's kind of blended in my work, other people's work. Of course, you know, I'm making very, very heavy attempt to present only thing that makes me look very smart and very good. And anything outside of it, I'm not either presenting or I'm saying, I don't do philosophy, I don't do this, I don't do life and death. So that way, you know, I maintain a good image.
Don't these questions come in your mind?
They come and they go away very quickly because I think it's, I'm trying to maintain my glucose and oxygen and all that quite well because pointless. I mean, you know, I really just, I get into trouble. I was telling one of the professors that I was meeting with my IIT classmates and this and that, and they are getting older like me and all that. And when people get older, they absolutely get more philosophical, spiritual. People like to want to know the meaning of life, belief in God, and these goes up when adversity occurs and all of that. And I keep having a rational conversation. I got very big trouble with my classmates. And then I had to say, back off, let it be, you know, because I want to break it up into rational, logical thought. And it's not that, and then somebody, one of them jumped in, so you're an atheist. And I said, not an atheist, I think one of the students are trying. It's not that, it's just get to the point, and what we don't know, we don't know. And I'm open-minded that maybe that's God and that's your belief, and it can be my belief too, because it's so mind-boggling. How could anything like this can in any way come together? Darwin cannot explain it. But that doesn't mean that we can deny the fact that the sun looked like God to people at one time. And it's no longer God in that sense. It's a fiery ball of plasma, right?
Because at a certain part of time, like this motion sensor kind of analogy, if I say, if it is not, if the overlapping is there, then we try to make the motion from ourselves.
Yeah.
Similarly, seeing at an static phase of ourselves, we do this kind of thought movement.
Yeah, we can, and I mean, I think again, we are all different, right? How many of you like music? Some like art. Some say I hate music. Aurangzeb, you know, we are all different, and some of you are free to and should think a lot about topics that matter to you. Who are we? My intelligence, human emotions. I have my own. I mean, you answered the question. We have a short life. I have some level of ability. I can't do everything. Let me focus on what I can, like educating you, right? You, for example, went to the local school and village to know how I can help the kids. Well, I'm doing equivalent how I can help you in your educational process. So I think we all take our own different priorities and perspectives. Okay, let's get back here. So what I'm going to show is, you know, this whole idea. I know it's going to be a little, because I hope that horrible sound doesn't come up. How can I, for example, you know, a lot of my work relates to prosthetics. So, and I gave that example a couple of days ago. So, a prosthetic arm needs to go and pick up the cup, and if the cup is vertical or horizontal, I won't know, right? So, the prosthetic arm, if I didn't have any other option, then I would go like this, and then I would grab it like this, right? Why would I do this? So, my other option would be do that. That's what an amputee would do. But what if I had a vision? Then, you know, of course, I would go like this. You know, so the point is that we have vision that's inherently incorporated, but a prosthetic arm doesn't have that kind of vision. So we put it in a.
One more thing, how does it think that it has to be turned?
Well, I mean, you know, it's a. No, we're not that far. It's none of that. I think what happens is that because a prosthetic arm is already connected to the person, right? So So it's not that arm is thinking, I am thinking, I'm going here. So arm has no choice, it's coming with me, it's that. And then muscle or EEG if you wish, but muscle signal does the contract. That's why I skipped some of the slides actually, because
the primary goal of
I was afraid of that. I didn't want to go back to onset, but when we come back, I'll show you the step by step, that myoelectric, so muscle signal control. Because going to EEG is pretty complicated and awkward. So if you can see here, that is actually there. There is a myoelectric sensor and signal that then goes and actuates open and close phenomena. But when and how I should rotate, that information could preferably come from vision. So
something I saw in the Valkyrie model, Valkyrie it was one of the professor explaining the model of Valkyrie robot humanoid. So he was having this humanoid hand also for these two different functions. One is this, and then the rotation component. One of the EMG was using from here, and the other one from somewhere else.
Yeah.
So those two commands are leading to two different movements.
Yeah, I mean, I have a whole entire lectures on prosthetics and control and so on. I mean, I just don't have enough time to go into this thing. But yes, you can do motor control, visual, EEG based control, all of that. I know one of you student here was doing EEG and EMG combined. So anyway, here essential idea is that you can see that that's the prosthetic arm, some touch sensors.
You can give 5 to minutes break for tea.
Oh, already we'll finish quickly. In fact, give me 5 minutes. Yeah. So visual tactile setup.
The embedded dynamic.
Oh my God.
A sample demonstration.
Jeez, this thing is relentless. Yeah, but it's still, yeah, I'll do that. Thank you. But it seems I'm worried that it'll start overlapping. All right. Anyway, it's now muted. We'll finish this slide in next 5 minutes so that you all can go for tea, coffee. And let's just jump ahead. That's just only the point I wanted to convey. I think we are done. So that it's like one realistic application. I showed you other about robot tracking each other, application in a drone. Now this is in a prosthetic hand, so in this case, the person is actually moving, and so you see the hand changed its grasp to pick up a mouse here. Although arm is being carried right now, it's not, it's in a stage of development, so we are actually just carrying and holding the arm. But you see, the thumb changed and rotated and adjusted to pick up the cup. So you can see that vision and touch can work together even without direct connection to the nerves and the brain. Let's do the questions during coffee and all, because he wants us to take a break. So of course there is an algorithm in neuromorphic about orientation, edge, and all of that, and then that algorithm is what's working so that we can do these things. And there is a lot of grasp in all that theory, and some convolution neural network goes behind it, but trying to make it biomimetic. Okay, so I think it's time for coffee. Yeah. Yeah, then I can just do my work here. Yeah. This receptor touch sensor is skin-like, is a spiking principle and some neural network. Are they for modeling people? This is our model. Is it accurate? Well, this receptor is a simplified version of Sauer-Hodgkin and Huxley. The point is, you apply pressure, produce spikes. If you go deep into literature, people will have modeled that relationship between pressure and spikes very well. Similarly, spike train, it's stochastic, random, which you saw in that lesson in the earlier video. Neural net algorithm, it's kind of rather simplistic. Ours is kind of like a roughly one layer neural network, but it teaches us something. So we'll see how it goes. So how do you approach such problem, right? So rational thinking, good science. Well, let's first of all learn the biology of this. Based on biology, for example, we can make sensors that are skin-like, then come out with these algorithms that are neuromorphic of spiking, and then there's learning and adaptation, all that happen, and then maybe we find an application for prosthetics or robotics or whatever. See, step by step we can develop this journey. So there are these cutaneous reality of biology, even this is probably simplistic, is that there are many layers. This is the upper layer called epidermis, and then there is a lower layer which has these different types of receptors called Meissner. It's specialized in slow vibration. Pacinian is for rapid vibration. Ruffini are deeper, and so when I really apply pressure, they might be activated. Some of them are free nerve endings at the top because they are for pain, right? Very sensitive. Heat, cold, reflex. Merkel for sustained touch, so that kind of slow, sustained, general touch, not necessarily pressure. And there are a couple others that are not as too common. Of course, there are blood vessels and hair cell, all of that. Even hair play a very good role. So whenever there is hair, we can perceive better. There are people who are materials, we have some materials people. Yeah, materials people are making the biggest advancements nowadays, making materials that are skin-like, including putting some nanofibers or microfiber that are hair-like. So all of this is all being developed. So let's, this complicated 3D thing, let's simplify it. It'll always keep coming. Keep it simple, stupid. Simplify it. All right. So let's we have some sensors on the top, some sensors at the bottom. That is one kind of unifying principle. So these are likely to be more sensitive to light stuff. These will be more sensitive to high pressure stuff. Secondly, there are fast and slow adapter, as I gave analogy, right? If I think, some receptors will, then after that they forget. And then I will remove something else. But these guys are pretty much constant. So we use both in a combination, slow and fast, to a stimulus of pressure. You see, there is some analogy to the vision. We look for the edges, we fill in the middle. Of course, if it's really important, we pay attention to the middle and detect color and all of those things. But generally, when I look at your face, this, that, and I don't go into the details of this. So it's the nature has sort of divided that way. It's a kind of rather simplified division. Of course, you can also see there is, this is too simplified, but even there you can see that there is some variation in this and all that. So it's really very simplistic. This really could be the real world spiking data. So you can see that there is a stochasticity to it, which means it's kind of random, but with you can fit some distribution. What's for theory people here, statistician, is what's called point process. Point, it's a point process. Time interval is what matters. And so it can be fit to a certain distribution called Poisson distribution. It fits it, right? Just like Gaussian is what you're more familiar with. And works reasonably well. Most spiking activity fit this point process, point process model. Here is an interesting observation. How would it be coded? Like when I touch, as soon as I touch, the receptor gets a pressure and a spike is produced. Does the brain detect an object based on, let's say, all the receptor and the first spike that comes out and say, yes, it's an object like this? This is again very highly simplistic, but the first spike itself could tell you that. Yesterday I talked about audio and spatial localization. Very first spike should tell you that, because if you wait for second, third, fifth, it will be milliseconds before they come in. So sometimes that first spike coincidence is what we heard in the ear, right? Sometimes it's entire spiking distribution. They're like a combination of it. So there are more spikes in the middle where there's more pressure, and that's certainly a way you can create a profile by looking at how many spikes. Of course, this will be slow to build up, but maybe a better reliable assumption of what an object shape looks like. So this is what is called first spike latency code, rate code. Again, we are just modeling. We are just speculating. If it shows up that with this I can detect object, the model probably is pretty good. Can I validate it? Yeah, maybe go and look at nerve signals and see if we can find that. But sometimes it will be very hard to record from these in 3D not easy to go and find these. These are microscopic things in a three-dimensional body. It's a nice picture, but in reality it's very hard. But some people devote decades of their life to model, experiment that, and information is available. So we are at more engineering scale. So okay, so now the touch. So we have all the receptors. So now I can put the sensors nicely located like a finger. As soon as I press, all the spike activity starts, and all that information from each pixel or each receptor is going out like this. And just like in a skin, there might be the first stage and then there is a second stage. By the way, a lot of modeling people, this guy called Roland Johansson, he is like the famous neurophysiologist, collected all this kind of data. Now anyone can model and do the design. So those who are doing modeling, that's what happens. You find some key, core, exciting papers that have a lot of information that you put it mathematically. So now we can put it in a neural network to see, and this is the way in the eye it goes from rods and cones to ganglion cells and amacrine cells, all of that in the middle, and then to the nerve fiber. In the skin also it's all the same. There are receptors in the skin, from that the cutaneous neurons, and which is the second order, and then there will be higher order neurons. So we can do that. And so I had shown some picture like that even yesterday for motor and sensory. When you get all these spikes, kind of very difficult to make meaning out of them. It's too complicated. So a lot of neurophysiologists, I mean, a mathematician can fit equations, computer science can deal with the data, but bulk of the work is done by neurophysiologists. Keep it simple. They said, okay, let me just create a distribution, and surely this distribution looks different than this from that, and they try to make sense out of that. And such a distribution might show a peak then and trails off, then you might say, oh, that's first arrival or fast. Maybe if it looks flat, maybe it's a slower adaptive receptor. So a lot of neurophysiologists done like that. Take a receipt, a lot of these spikes, and create a distribution. Okay, so now let's switch to real world engineering. So let's make a tactile sensor out of it, something we learned a little bit from biology. Let's make biologically inspired sensor. So this is a tactile sensor. So we can make it out of some type of fabrics or whatever, but what do they have to do? Mostly we are generally able to do this electrically. So maybe if the sensor can change its resistance or capacitance with touch, then we convert that change in resistance or voltage or capacitance into spikes. So the change is, it's through a property of something. Something when you press, like maybe this is a foam like material on which my sensor is put. When I apply pressure, its shape may change, its resistance may change. If it's piezo, it will produce voltage. Of course, there are some other unusual electric and magnetic as well. But by and large, that would be our sensor. So what can be a sensing element? It could be resistive, like a strain gauge, piezoresistive, which means it has that piezo effect, so the force converts into change. Capacitive, two metal plates, so when you press, the capacitance changes, because that's how capacitor work between dielectric as a piezo material, and then very rarely this magnetic, optical, ultrasonic. Fabrication, you can make this sensor, this kind of conductive sensor in a polymer. So this is like a transparent polymer, like what's called silicone or PDMS is a name. It's another kind of soft polymer, and people put metals on it so that you can implement the sensor. More lately, because people are very interested in wearable and all of that, so fabric-based sensors. So now, like fabric itself is touch sensitive. In consumer area, people are starting to build sort of smart clothing. You touch and you can type on a cloth. It's the same. That's why this is important, because touch sensors like this put on a fabric, and if I can now type, so I don't have to have a keyboard, that will be great, right? Or by touching, open the door, close the door, whatever. So there's a commercial interest in these smart fabrics. Not so much killer app, but it's out there, and probably increasing, and more it's going to happen. So the synthesis of textile industry and electronic industry is occurring. They're going to look for biology for some inspiration. So, I think I showed you this. So, fast and slow adaptive. So, now our algorithm is going to start working. So, we made this out of fabric. So, this is like a two-dimensional grid. It is a piezo fabric. So, apply the pressure, changes the resistance, produces the spiking activity. That is the electronic circuit. Applying a threshold, you can convert these into spikes. Then put some biologically inspired algorithm, and then hopefully some decision in a robot. So, what is the algorithm? And so, this is like the simplest way I can explain to you how neural network is, right. Biologically, you can relate to, right, this is a neuron, it is sending out all these dendrites, it is connecting to other neurons. In this case, we have shown dendrite to dendrite connection, but dendrite could go to soma, everything. Spikes are coming in. So, the value of the spike and how much influence it will have on this dendrite, so that to this neuron is modeled by this weight. How strong is that synapse? And the learning is that this synapse gets stronger if it is used. So, use it or lose it. So, it gets stronger. The weight may vary depending on how at the tip or somewhere deeper it is, and this adjustment of the weight is what is going on. Even as we live, cells may die, then a lot of it goes with it, cells, but you do not get new cells. So, everything happens by rewiring the weights. You can almost imagine that if I were, there are two ways this could go. This neuron is taking data from here, summing it up in a complex manner to make a decision. But what could happen is that this neuron, suppose it dies, then it could learn to adapt with these weights and restore the sensory information. It can learn by lots of reinforcement. This might start becoming stronger for future use. So, in a neural network, what is called synaptic kernel, we implement this, right, nice one-to-one mapping, neuron 1, neuron 2, weights, there is some kind of sigmoidal kind of nonlinear transfer function, goes to the output neuron or its soma, again sum up all the weight, apply some threshold. If all of this adds up, strength of this, the weights, signal is big enough above a threshold, then you produce a spike. So, it is an intuitive way to understand how neural networks work. Now, in reality, of course, this is a two-layer, but it could be multi-layer. In biology, input might come thousands of things. Instead of neurons, it can come from receptor, but you get the idea, right. Maybe let us, for tactile sensor, let us call it a receptor, first layer neural network, second layer decision network, make a decision, produce a spike.
How the threshold is decided?
They are biologically, they are what nature gives us. You saw that action potentials, Hodgkin-Huxley type went from -70 to +20. Some cells it is -80, some it is -20. From -70, you have to go to about 5 to 10 millivolts before the threshold kicks in. I had shown you some things like that. So, the same way here, you set up some of them empirically based on how sensitive or unsensitive you want to make. If your thresholds are very low, it will be very sensitive, because only small change will trigger spikes, but it will be very noisy, because a little bit of perturbation will do that, right. It's the same thing, right. If you are, and we are doing this very adaptively, right. You can try it on yourself, right. I mean, you touch, you do not care, but if you are tuned to it, I feel it, lightest touch you feel it. What did you do? You change your threshold, you are adaptive. See, you learn, your brain, mind return the information to say, feel the lightest touch, because the need was there, versus other time, I do not care, so the threshold disappeared. So, that is adaptation here, but there is adaptation there also. Okay? So, it is empirical based on how sensitive you want to make the sensor noise immune.
So that propagation happens in biological networks also?
It depends on how you look at it. In the cortex, so there is this there is a network. Do we really know that it is layered? Well, we know with layer 1 to 6, but it isn't like precisely go from here to there. I mean, layer 4 cell, I may have mixed it up, but layer 4 are, let us say, input cells, large pyramidal cells getting the input, and layer 5 are the output cells. It is a simplification, because more likely than not, one of them is producing the output, other one is integrating. That shape looks like that. But other layers have role to play. We just, I don't know enough, we don't know enough. Interneurons have role to play. Is there a back propagation within that? Seems like they must be talking to each other, right? Neuron in this goes up there and comes down and makes a synapse to go to that, which may be in other layers. So that is a kind of a back propagation. But I don't think that there is a physical deep learning. So deep learning, deep kind of idea is that there are multiple convolutional or recurrent neural. That I don't, physically it's not there, right? Physically brain isn't under so many hierarchy, but functionally it could be there. So functionally means message goes from this neuron to that neuron to that neuron here, there, and it might be many deep. Yeah.
So isn't the learning in the brain local rather than a global supervisory signal as well?
Everything with everything. Everything is possible, right? I mean, surely easy to understand is local. If a visual input comes in, that pixel goes to a particular part of brain, I mean along the way certain nuclei, and from there goes to some part of the cortex across layers. It's analyzing an individual pixel, but individual pixel would make no meaning unless you associate thousands and millions of pixels together to create an image, which makes no sense until some further up sees that image as a face and a higher level cognition. So surely that a lot of it is actually largely global, because a lot of the higher level association is global. Lower level is probably local. So tactile lower level is receptor one-to-one spiking, but higher level is texture and shape. Now you ask the question learning. So learning is at every step, right? Learning is happening at the synapse and synaptic strength. Learning is occurring on the transduction of how much change in voltage means how many spike activity. Then every step of the way neural network keeps reinforcing itself. So learning is like that. Learning is in hippocampus, which is one kind of learning. Learning is highly distributed, so it doesn't matter what happens, you'll remember some part of the brain, the information they'll take over. Even if people get stroke, their old memories are left, but sometimes in a stroke memories are lost. So these kind of learning and memory are at a very technical level. I broke it down as synapse, spike activity, strength. At a meta level, it's highly distributed in the brain.
My question was basically any change in weight in the synapse would basically mean would be because the back propagating action potential.
No, the back propagation is not as much as it made it out to be. It was an idea as a theoretical thing. It's very hard to prove that there is a literal back propagation in anything other than calling it a sensory feedback or complex network. In reality, 3D brain isn't structured like classic neural network front run. There are back propagation to somehow learn. Quite often there is no back propagation. There is a one-shot learning. There is a certain experiential learning. There's probably cross correlation matching. So I think back propagation is one of the popular programming tricks. That's all you should be able to say. Don't try to give it too much biological meaning. Okay? Literally, there is no circuit to go there and then create a back propagation to improve my sensitivity. I mean, that kind of wiring, hard to imagine that exists. There are some like spinal cord reflex loop. That's front back is quick, but otherwise it won't be so easily available. Okay. Okay. So as I said, there can be many types of coding. You know, even telecommunication. One of you is doing, come from electrical or telecommunication background. There are many ways to transmit data. You know, there are many ways to do sound, AM and FM, pulse code modulation, pulse rate modulation. There are many ways to. So we don't know. Brain, it wasn't invented with rate coding by some god, right? I mean, it's how we interpret data, and so brain data is stochastic. So it might be easier to associate with things like rate and temporal and so on. So rate means lots of very high frequency at this time, low frequency, or it could be temporal. These are slow, these are fast. So all of that code can come out like this, and now I have a rate coding, right? Slow, fast. really slow. That could be, or I could do temporal coding. See, essentially the first spike where it occurs, I gave it a shape. By the way, it's impossible that it will be so literal. It will be also within that it will be stochastic. Certainly, it won't be like 10, 20 fibers. There will be hundreds of thousands of fiber generally carrying distribution like this. And then, you know, we can rank it in relative importance. So, these guys in this case temporal coding have the shortest latency because they are fastest, and we give it a 1. In this one there is another way to coding. So, you know, this is the way we weight the information. Well, it's fast, must be important, let us give it a really good weight. So, those who are writing computer programs could take advantage of this information to write a code for fast and slow and all of that. So, as I am touching, see, I am touched and I created these spikes and pressure waves. Fingertip have very high dense innervation. So, this dense innervation will give us that spiking information that goes up further up the chain. We have not as much cells, tactile sense, that density is lower. It's amazing how we can just, I mean, I sometimes think about it, right? I mean, I can exactly know where this is, or if I have to itch, oh, it's itching here. Can you imagine how that brain map must be? There are not that many cells in hippocampus or whatever, but somehow we know that I am touching here and that is where the itch, and when that information goes and I scratch, itch goes away and there is a loop. So, all this information is mapped somewhere in the brain. Not so fast, by the way, it is all slow. And so, now our sensor is working in a more practical manner because it is a multi-layer sensor. This is the electronics to go with it. So, it compares the voltage, produces the spikes, and so this is actually the pressure profile, and you can see that brain may create a map like this, or robot might benefit from a map like this. If you robotic palpation, you could use it for palpation for medical application. So, there is a little bit of more of the electronics, multi-layer, piezo fabric, some electronic switches, electronic amplifier and comparator. And now, from this, let us put it in practice. So, you saw this video a while ago. So, this is that flexible E-skin, fast and slow, adaptive, based on colors, say highly responsive, and little tiny dots are our spiking activity as if like they are going up to the nerve. Okay. And so, when we do that, now we can apply it to robotics. So, everyone loves this video. Oops, eggs break, no touch. The student did a neat thing, he put a tiny hole in the egg, because otherwise it will become very gooey. Okay, by the way, so with touch sensor, shell does not break. So, what it did is make a tiny hole and took out all the yolk, and only shell is left. But it illustrates the principle that with a touch sensor, now this big metallic hand can deal with egg shell. Beyond that, we can look at shapes, see, object, spiking activity, from that at a higher level construct into shape. And then all that went into a chip, it is called the Extreme Learning Machine, ELM. It's a one kind of neuromorphic chip, very simple, it's brute force, single layer neural network, no black proc and no learning, which are arbitrarily selected, very quick, and it works. By the way, it was not as if we are geniuses that invented ELM or something, it was just a coincidence. Another colleague nearby, he was actually an IIT Kharagpur graduate. He had built this ELM for totally unrelated application. We kind of put 2 and 2 together. So, a lot of it is sometimes you have to take advantage of what's around you, you know, because very common mistake. I'm giving advice to you, right? Every student wants to be a pioneer. They want to start on their own. In the first year looks great, second year looks great. In sixth and seventh year it doesn't look great, and say, why did I do that? Join your senior student, help them. If one of my, this is all great, but I really want to work. I have actually a PhD student at Johns Hopkins. This is all great. I want to work on proprioception. That's a sense of positioning. It's going to take 6-7 years to ramp up to from basics. If he goes here, now he can, from shape, he can go to texture, make more rapid advancement. This happens to be a single layer tactile sensor, but let's make it multi-layer sensor. Replace ELM to the next higher level. So yes, it's great to be a pioneer. I mean, any one of you can be Ramanujan and Einstein and not follow the crowd and not follow the precedent and come up with brilliant ideas. For most people, you build on prior work, preferably in your lab so that you can have foundation to build on, or making sure that there are collaborators and resources available. And lastly, if there is an information literature, advisors. People further away have only limited interest and time. So you really have to make sure that when you do anything, you have the facilities, advice available. So now from this, we can build a lot of different things, texture, shape, palpation, whatnot. So in this case, now this is our more multi-layer network. So in this case, input node, hidden layers, output nodes, which would be a bit more useful in this prosthetic arm application that I already discussed. And so, you know, we'll play the video again with this time no big noise and mess. So. It's nicely adaptive. That itself was about 1 year of work, but it's pretty good. Okay, I think this is a audio video system, so let's try this.
This video shows the design and fabrication of a vibrotactile haptic glove. This work was done by the Neuromorphic Engineering and Robotics group at the Singapore Institute for Neurotechnology, SINAPSE. Haptic feedback is the rendering and replication of the sense of touch to allow an operator to intuitively perceive and understand a distant or inaccessible environment. Haptic feedback is mainly rendered in two ways: force feedback or vibration feedback. The motivation for this work is enabling human perception of remote robotic environments. To achieve this, we have developed vibrotactile haptic gloves using vibratory actuators placed at sensitive locations on the hands to deliver precise and localized feedback. The actuators were embedded on a flexible PCB. The communication pathway is initiated by transmitting an encoded stimulation signal generated at the computer terminal. This signal is received by the control box embedded within the glove. This signal controls the vibration intensity of the actuators. We have developed a graphical user interface to enable single and multiple actuator activation. We use amplitude modulation to control the vibration intensity of each actuator.
I think that's it. But you see, so sorry, I should have given preamble. So it's all good that you have
sensed. It is wirelessly connected to the glove to enable custom actuation patterns.
So point is that you have sense of touch. If a doctor is wearing a glove to palpate, or let's say somebody wants to do tumor or breast cancer or that kind of examination, the subject is reluctant by being touched by whatever male or some unknown. Well, let a robotic hand do the tactile palpation. But how do you get that information back? And so what it's saying is that one way is that a doctor could be wearing a glove where the vibration would go provide a feeling. The other is could be visual, so that you can see the visual graphics on the hand and you can see where there is soft and hard and bumpy and not by palpation. It's a haptic feedback is an evolving field. Say for example, our phones at the moment, there might be some phone that has started to have the feedback. But you know, we do have a feedback when there is an alarm, like it vibrates, right? But otherwise, our phones have touch sensors, but they don't have haptic or vibration feedback. And surely it's coming. That way, now you can send your feelings, like I touched, a little vibration goes to the other side, person receiving the phone, and you feel that vibration. If you have an agreement, what that means, you know, I like you, I hate you, whatever, right? So haptic feedback is likely to evolve into an interesting area. It's kind of limited because these motors and vibration and all that cannot be micro miniaturized like sensors, but it's very appealing in telemanipulation and communication.
In addition, we have developed an electronic skin to provide a robot end effector with a sense of artificial touch. The electronic skin is an array of pressure sensors constructed from piezo-resistive material. The electronic skin will be integrated with a robotic end effector such as the ILM robotic hand developed by Touch Bionics. The tactile sensors on the robotic hand will provide information about the pressure distribution of the object being manipulated by the robotic end effector. The sensorized robotic hand will be interfaced with the haptic glove. Depending on the amount of pressure applied to the sensorized robotic hand, equivalent vibration will be experienced by the user. For example, low pressure input to the sensorized robotic hand will produce low vibration intensity on the corresponding actuator.
So you can visually grade it. You can
Similarly, high pressure input will produce high vibration intensity on the corresponding actuator in contact with the user's hand. Precise rendering of artificial tactile stimulus has important applications in the domains of telerobotics and virtual reality.
Okay, so that's how this kind of program works. I think this is probably it's okay. This is a robotic. Oh, it's not a video, but using this kind of feedback, the robotic hand is cutting a bread, you know, because it can feel and palpate such things. So this can be application in telemanipulation, underwater, all kind of things. I think that's it. I think I covered all that. Okay, so I think there's a lot of course, there's a neural network theories behind it. I don't cover deep network, convolutional network. You can apply all of these in the future. Okay, so we are 10 minutes to 1. We could start breaking up and maybe we're just so short of time. So we'll see. Try to come by 2:30. If I'm done, I'm done. Okay. Let me ask you this. I know this whole business of quiz, and again, Professor Debasis isn't here, and it's sort of required by the government, lecture, that you guys be tested. I don't think it has to do with pass fail, but it has to do with sort of feedback on knowledge acquired and how effective it was and all of that. So we're going to do it, and it'll be good exercise for you to review in a way. My quiz question will be pretty much some iterated version of what I've given you, so don't get stressed. But let me ask you this, because we have only so much time. We have about at most 2 hours today, and you know, so even if you meet 2:30 to 4:30, I can cover cognitive engineering. 4:30 to 5 quiz, or 2:30 to 4, I can cover cognitive, and then 4 to 5 quiz or something, and then we break up. Although we can go until 6, but Kshitij program you might enjoy. And then we have about 3 hours tomorrow, which is just general overview. It really would be helpful for me to know what do you want, right? Not what I want. So I can ask Professor Debasis whether quiz can be postponed till tomorrow. I don't think so, because they need to grade them tonight, so we can finish all that. Do you need? Let me just get a sense. Please vote. Get a sense of numbers, and I can imagine divide, but we have to make a decision. Do you want more lectures for something more, or more discussions? More lecture? How many for more lectures? Okay, and how many for like general discussion, Q&A, meaning of life? I mean, I don't mean anyway, so much smaller number. So I think we will then, yeah, so if I obviously can't cover some of the material, then I can go to tomorrow. Like I said, I like to review, but I could try to dig out some advanced topic. Again, if you don't want to expose your identity, just leave a piece of paper here and write something. I want to know more about this and see. So what I haven't done, other than a very superficial sense of some of my research, in many topics, I mean, there's a much, among the things I've described, there are more advanced stuff I could dig out. So tomorrow I have a lot of flexibility from going from repetition to even introducing something new. I can try. I mean, I cannot guarantee. We'll probably lose about an hour in formalities, you know, and so we have about 2 hours tomorrow and about 2 hours today. So I think 1.5 to 2 hours. So I'll use that for cognitive side of things, and 2 hours tomorrow. It'll be more lectures rather than one-to-one discussion. My plan this evening for how do you want to just go around, walk around the campus. Everybody's saying this Kshitij is great. I don't know, you know, it's really the first day, so most likely what we'll see is young students. You see the campus has already become very busy. Lots of people have come from other universities. So I'm sure they're probably getting started on the project, so maybe they're just going to demo and build up, or maybe the competition starts. I don't know, it's a 2-3 day event. Sorry?
From tomorrow onwards, the competition will start.
Yeah, so today it'll be just setting up.
It's more like registration and inauguration.
Sorry?
Registration and inauguration.
Today.
Yes.
And one guest lecture is there.
Oh, that's it. There's nothing going on.
There's an inauguration ceremony.
But that's all.
That's it. It's all formal.
So what happens if we go?
Formality kind of lecture.
Sir, from tomorrow 7 o'clock, that the games and those things.
In the evening.
No, 7 a.m. From 7 a.m. tomorrow, you have a flying RC competition which happens in a big stadium.
Everything